So we did a lot of stuff on fault resolution. And at that time, we were really just doing geometry to resolve the stress on a fault. But we really didn't know why or when, the fault would actually slip, okay? And so the sort of criterion or equation that we typically use for when a fault will slip was actually part of the second question, or one of the questions on your exam, right? I gave the equation and sort of set up a scenario, but in this case, this is the equation where you have the shear stress and the normal effective stress resolved on the fault. So these are the shear and normal effective stress on the fault is equal to some friction coefficient. And so you have this Coulomb failure function, which just rearranges this equation and says that basically, as long as this, where this mu, and this shouldn't be confused with, the one we used previously, ui, which is sort of a material property or the strength of the rock. This actually is the friction coefficient, right? So we're not talking about mu I, the internal friction. We're talking about the actual friction on a fault, okay, as measured in the laboratory. So this is, again, a material property associated with faults or associated with friction. So it has to do with basically the surface roughness and other things, the types of material, the surface roughness and other things. And so basically, if this function is less than 0, the fault will not slip. If it comes equal to 0, then you're going to have slip. So here's a range of data. This is a little hard to see, but I mean all of those dots represent tests done on friction tests done on different types of rocks. And what we can see is that in virtually no scenario, I guess these is, if you can't read this, this is the normal stress versus shear stress. And so in almost no case, virtually no case, is this friction coefficient, that would be the slope here, this friction coefficient less than 0.6. So what I'm really saying is, in no case less than 0.6 did this ratio of normal to shear stress on the fault cause it to slip. Right. And so, and again, these are a bunch of different types of rocks. So basically, we can come up with some bounds that say that coefficient of friction is always less than or equal, always between, rather, somewhere between 0.6 and 0.1. And so this is the 0.6 line. This is the 1. Okay. So coefficient of friction for rocks is always in this range. And a lot of times we just say it's 0.6. I think in the Zoback book he makes a curricular remark about this guy Jaeger, who was one of the most famous guys in rock mechanics for all of the last century. And he had a saying or something about, there's 2 things you need to know about friction. It's always 0.6, and it'll make a monkey out of you. So anyway, basically saying it's always 0.6 until you need it to be, and then it won't, and then it'll make you look like a fool. But virtually, if you don't know any different, we always use 0.6 for friction, and it's not that bad. The data doesn't certainly that's a bounding limit.